All right, let's tackle another interesting question, question 248. It is really similar to question 246. And by the way, it is a good idea to practice this question. There's a lot of material and it's complex if you don't know how everything tied together. So let's read the question. 248. A city consumes an average of 100 megawatt of power at a voltage of 10,000 volt. L1, L2, and L3 represent the transmission line, and T2 and T1 the ideal transformer. The transmission line are made of aluminum with a resistivity of 2.7 multiplied by 10 power minus 8 ohm meter, and a cross-sectional area of 0.001 meter square. The transmission line L1, L2, and L3 are respectively 1 kilometer, 1,000 kilometer, and 2.5 kilometer long. Given the ratio of number of turns from T1 and T2 are 30 and 1 divided by 20 respectively, find the input voltage of T2. So input voltage of T2 will be the voltage here, the input voltage. B, the output voltage of T1 will be the voltage over here. C, the power being produced by the power plant. All right, let's make sense of everything we've been given. We've been given the length of the first wire, it is 1,000 meter. The length of the second wire, it is 1 million meter or 10 to the power 6 meter. The length of the third wire, 2,500 meter. We are also told that at the city, the power consumed is 100 megawatt, so 10 to the power 8 watt. The voltage consumed at the city is 10,000 volt. So because we are given the length of each wire, and we are given the number of turns of each transformer, we can right away find the resistance of each wire and the current through each wire. These are the most important information. We should find them right away. It will help us throughout the entire problem, and that's what we're going to do. So let's start first with the resistance. So Ri is equal to the resistivity multiplied by the length of each individual wire divided by the area. Now note that they share the same resistivity, the same area, and most likely in a test, I will give you same area and same resistivity. I don't want anyone to be confused with these values, but I want to make sure everyone is able to find the resistance from these values. Okay, so that's important. So again, it is equal to 2.7 multiplied by 10 power minus 5. Just to make sure, yeah, there's no mistake there, multiplied by the length in question. So using that formula in the given length, we can find R1, R2, and R3, and I'm gonna write them on the left side over here because they will be needed throughout the question. So R1 is equal to 0.025 ohm, 27 ohm, sorry. R2 is equal to 27 ohm. R3 is equal to 0.0675 ohm. All right. Now the goal is we want to find the current I1, I2, and I3. We already can find I3. This one is fairly straightforward because just like we did in the previous problem, we can find the current by taking the power divided by the voltage. So the power that we need for I3 is the power consumed at this city. Now note that the current at this point is the same throughout the entire wire. So I3 is equal to the power consumed by the city divided by the voltage consumed by the city. So 100 million divided by 10,000, we get 10,000 amp. I'm gonna write it over here. So I3 is equal to 10,000. Now note, I'll omit the unit over here because I'm running short on place, okay? But I3 is 10,000 amp. All right, so we want to find I2 and I3. And basically what we're going to do here to find R2 and I1 is to use the ratio of turn from the transformer. So note, we will start with the second transformer because we already know I3, and I3 is linked to I2 through this transformer over here. So the ratio of turn on the second transformer, so the number of turn on the secondary divided by the number of turn on the primary, is 1 divided by 20. This is also equal to the current, the primary current on the second transformer divided by the secondary current on the second transformer. The primary current on the second transformer is the current coming in it is I2 in this case. Now, just as a reminder, I didn't mention it in this problem, but the logic is identical to the previous exercise that I solved. I1 represent the current in the first wire, I2 the current in the second wire, I3 the current in the third wire. Same logic for V1, V2, V3, and R1, R2, and R3. Okay, it's all related to the wire. When I'm talking about the power plant, I add the subscript PP. When I'm talking about the city, it's VC. All right. Okay. So the current coming out. So the secondary current from the second transformer is I3. So we replace these terms. And basically what we find is that I3 is equal to 20 times I2. Well, that means I3 divided by 20 is equal to I2. I2 has to be, well, I'm going to use the other marker. So I2 is 500 amp. All right. So I'm going to erase this section. If you need to pause the video, do it now. And we're going to repeat the same process for the first transformer to find the first current, I1. So we are given that the first transformer has a ratio of turn of 30. So NS1 divided by NP1 is equal to 30. Again, we can link this to the current. So it's equal to IP1 divided by IS1. IP1 is the current coming in. It is I1. IS1 is the current coming out. It is I2. So basically we already have I2. We know that I1 is equal to 30 times I2. I2 is equal to 500, so it's 30 multiplied by 500, and we get 15,000 amp. All right, that's good. So now we have the current in each of the wire. We are equipped to find the remaining piece of information. So it's 15,000 for I1. All right. I'm going to erase that part now. We don't need it. Actually, we will need the voltage drop to solve the question, basically. We will need a voltage drop in the third and second wire. We don't need the voltage drop in the first wire because we are asked to find the voltage here and the voltage there. So let's find V3 and V2. So basically, the voltage drop through a wire or any piece of equipment with an electrical resistance is equal to the current multiplied by the resistance. So in this case, I3 multiplied by R3. And what is this value? So 10,000 multiplied by 0. So I get 675 volt. So that's the voltage drop between these 2 points. Note, the current is going in that direction. So that means the voltage is higher here than it is here. Let's just highlight what that means. What that means is the voltage here at the beginning of the wire has to be equal to 10,000 volt plus 675. So it is 10,675 volt. Let's use the same logic to find V2. So V2 is equal to I2 multiplied by R2. In this case, it's 27 multiplied by the current, which is 500 volt. So 500 multiplied by so. No, okay, there's a. So 500. Okay, that seems right. Okay, that's an enormous amount of voltage. Oh yes, okay, that's a step of voltage. For a moment I was worried because this is a very big number of voltage, but I forgot that yes, around here it will probably be near 10,000 volt, but this one is a big step of voltage, so it will become a much higher voltage than this. All right, so we got V2 over here, and V2 will be used, once we find the voltage here, we can add V2 to find the voltage over there. All right, so let's go back to the formula for our second transformer. So we got NS2 divided by NP2 is equal to 1 divided by 20. 1 divided by 20. This is equal to VS2 divided by VP2. And we already found the VS2. It is the voltage at the exit of the second transformer. It's 10,675 volt. And we can find VP2 now. So VP2 divided, actually, flip it on that side. Oh, yes. Okay. So VP2 is equal to 20 multiplied by 10,675. Let's see what is the value over here. So we get 213 and 500 volt. So this voltage, just need to reopen my computer, and obviously it had to crash while I was filming a video. So yeah, okay, so this is our answer for part A. The voltage here, I'm gonna write it on the board. So here we have 213,500 volt at this point, and it is the answer to part A. Again, I'm going to be erasing, well, only this section. We are nearly done with part B. Part B will be very simple. So we are asked to find the output voltage of T1. So we need to find the voltage here. And basically, we simply add this value and this one up together. So I'm gonna erase the bottom part now. All right, so the voltage, and this is VP1. So VP1 has to equal the voltage here plus the voltage drop in the wire. So it is equal to 213,500 volt plus the voltage drop, which is 13,500. And basically what that means is the voltage at P1 is equal to 227,000 volt. So that's the answer to part B. So if you want to write it down, just confirmation, yes, it is the right answer. Okay, now we need to find to solve part C. We are asked what is the power being produced by the power plant itself. So let's have a look. I'm gonna erase again all this section. We don't need it anymore. All we need is this value and this value. So again, pause the video if you need to write anything down. All right, so the total power, I'm gonna use another marker. So the total power produce, so the power of the power plant, so I'm going to write P and subscript PP for power plant, has to equal the power being consumed everywhere. So power being consumed in the first power line plus the power being consumed in the second power line, in the third one, and in the city. So it's equal to P1 plus P2 plus P3 plus PC in this case. Now note, we already, no we don't have that value. I'm stopping, I thought we had a simplification here, which is not there. Okay, so we can input all these values. So the power of the power plant, and we replace the power by I squared multiplied by the resistance. So it is equal, the power in the first power line is equal to I1 squared multiplied by R1. And same logic for the other one. So I2 squared multiplied by R2 plus I3 squared multiplied by R3 plus the power consumed at the city, which is 10 to the power 8. Okay, so when we combine everything, we take the number we have acquired throughout the problem, and we get a value of 119.6 megawatt of power being produced at the power plant. So it is still a very long problem to solve. The only difference here is we need to take into account the voltage drop across the wire, okay? So as you've seen by now, each step is not too complicated, but we have many steps, and you need to understand how to put everything together. And like I said, these questions, they are very nice. They combine so many concepts together. Make sure you practice them, all right? So basically, we are done with the semester. We have covered everything. So if you have any question regarding anything we've seen in the course to get ready for the final exam, feel free to ask. I'm here to help you, all right? So see you in class.